Thanks, Robert. Thanks very much, everybody, for coming along to listen to what I've got to say. I've got too many slides for the half-hour slot that I've been allocated, so I'll do my best to get through them. Might have to skip ahead on one or two, depending on how I go. Lisa's hopefully going to give me a heads up when I've been talking for too long, and I'll try to wrap up as quickly as possible. Thanks for getting here on time. I wanted to give an introduction to some of the fundamentals and practical applications of laser vibrometry, which is my key area of interest, research interest and activity, and has been for many, many years, decades in fact, leading up to this point. Here's a slide that tells you what I'm hopefully going to be working through during the course of the next 30 minutes. You can read, so I won't go through them point by point. But what I want to kick off really with is what is it that fascinates me about laser vibrometry? Why is it the thing that I'm really focused on? Hopefully inspire some of you as well as to get involved with my research more. I already am collaborating with a good number of you in the room, and there are many, many more opportunities, I believe. This is, as I see it, a fundamental enabling technology. Indeed, optical engineering is in generally, so it, to me, sits horizontal across a range of application domains and other research strategies that we might want to engage in as mechanical and mechatronic engineers. Essentially, what we say about laser vibrometry is, it's a non-contact surface vibration measurement technique, and if you can see the thing that you're interested in, then you can make a measurement from it. There are some constraints to operate within, of course, as there always are, but we've historically talked about being able to use this technology, therefore, to be able to make measurements from hot, light and rotating structures or systems. This was a sort of an early-ish catch-all, if you like, for why would we want to use laser vibrometry instead of traditional contacting transducer techniques. And these are obvious applications. Contacting transducers more often have some kind of signal processing electronics within them, so you can't stick them onto the primary exhaust cylinder output. Light systems, it's a no-brainer. We add mass, we add stiffness to a light system by attaching a contacting transducer to it, and we change the characteristics. And rotating systems are everywhere amongst us. They power the world that we live in. Without them, we'd be completely snookered. Putting contacting transducers on them is not so straightforward. It's much more preferable to be able to make measurements of the vibration of these systems without having to attach anything. More recently, we start to talk about contexts of the measurement whereby we can make remote and or high spatial resolution measurements and or high frequency operation measurements. So in terms of high spatial resolution, we're talking about sub-micrometer laser spot size that we can put on any surface, and of course move that progressively across the structure of the surface or the surface of the structure to build up a high resolution, high spatial resolution vibration survey of that structure of interest. And in terms of high frequency operation, these systems are good for up to on the order of gigahertz frequency range. So there really is no theoretical upper frequency limit because the frequency of light is on the order of terahertz. We don't measure that frequency shift directly that we get when the light is scattered from a moving surface. I'm getting ahead of myself because this is what comes next, but it's a bloody high frequency, the frequency of light, and so physical things don't vibrate anywhere near as high as that frequency. And then a whole growing range of fascinating things that we can do with our vibrometer, and I list a good number of them in here, and I highlight some of those that I've already described and some of them that are particularly of interest to me, including some sort of espionage, eavesdropping, reconnaissance mission type activity that we might be able to do with these things, because we can use them to listen to what's happening either inside of a room or in a vehicle or somewhere, because of the fact that sound pressure creates vibrations of flat panels, and I can put my laser beam on that flat panel and theoretically not even theoretically, we demonstrate this on open days for students coming through our labs. We listen to what's going on in the demo in the lab next door and thoroughly fascinate them. Well, at least I'd like to think we do, maybe we don't, and maybe we just bore them to tears. But anyway, they choose to come here, so hopefully we're doing something right. And then some work that I'm doing with Sebastian, who's in the room, on termite vibrations, for example, are pretty exciting applications. We can learn many things, we believe, from the nature-inspired techniques and technologies that have been evolved over millions of years, let's say. And in my previous life, I was very focused on things that vibrate in terms of sports equipment and balls, which we can't attach contacting transducers for the nature, due to the context of the nature of the experiment or the measurement. So that's just a real snapshot, a whole bunch of other things in there, some of what we're doing more frequently, more recently, micro-electromechanical systems, for example, with nanometer scale resolution or lens scales in these types of devices, engineered in such a way that one individual finger or tine on this cone vibrates with a certain resonant frequency, brake squeal applications, for example. Even indeed making measurements of the sound pressure radiation through a fluid medium, which might be water traditionally or increasingly more air. Okay, so actually we make a measurement of path length difference with a laser vibrometer, and any fluctuations in the fluid medium through the path length of the laser beam we're sensitive to. These instruments are clearly highly sensitive devices, but industrially viable and robust. So we can make measurements from sports balls and pieces of sports equipment, and indeed from things that we're all very familiar with. And the automotive industry has really driven the development of these solutions. They will all have scanning vibrometers with at least one dimension, if not 3 dimensions. So there are 3 heads here organised around some sort of a triangle or the vertex of a cylinder, and we can make 3-dimensional non-contact vibration measurements across this entire structure. Here are some measurements of my own that are, in this case, yet to be published. So the sports racket, tennis racket scenario that I previously described. And with the 3-dimensional laser vibrometer, we've typically, with a 1D system, been able to make measurements of bending modes and torsional modes, for example. And this is real experimental data. It looks like it might be coming from finite element analysis just due to the spatial resolution of these mode shapes. But they're indeed done by experiment. We can make measurements from strings of vibration, of rackets, of musical instruments, for example. And this is a bending mode, so predominantly it's an out-of-plane vibration, but with 3D vibrometry you can make in-plane bending mode vibration surveys. And the hypothesis being that the sound that a tennis racket makes, which is critical in terms of whether or not we select it, is a function of... How can I help?
Sorry to interrupt. I just wanted to know if this is one-shot measurement from your vibrometer.
No, these are done sequentially. So we survey the target of interest over a series of individual measurements. There are multiple point vibrometer systems becoming available, up to 48 channels, but these are done. This is not a whole field measurement. It's a discrete measurement and it's built up. So there are some constraints around how we make that measurement, of course. We need to have stationary vibration that we can repeat from one measurement to the next, and typically we'll take multiple averages at each point to build up a survey of this type. Okay, so it's important how these structures sound, and therefore, as automotive manufacturers and OEMs do, sports equipment manufacturers invest heavily in the R&D around engineering the sound of a racket, of a club, of a bat, of a ball. And here are some example mode shapes that are animated. Okay, so this is, we go from one point to the next. You can see the point of the vertices of the lines, essentially. So there's around about 50 points on this system presently. Torsional mode, and then string bed only mode. So these are the first measurements that have been made of string bed vibrations in 3 dimensions. Again, the orthogonal string bed mode for that vibration mode. In-plane bending is interesting because the hypothesis is that the string bed, in the string bed mode, string beds might drive the frame, and it's the frame that can generate sound pressure. Meshes, as is the nature of the string bed, can't generate any sound pressure, but like a guitar, if the string vibrates, it drives the structure around it, and it's that makes the pressure that we hear when we strike the ball, well or indeed badly. Here are some other examples with relatively high spatial resolution of some Malaysian gamelans, which is a type of gong, and we made these measurements to fit to numerical or analytical equivalent measurements or predictions of the vibration frequencies, and you can see fundamental mode that's like a diaphragm type mode, and then a pair of diametrically opposed like second order, second bending modes. Other things that I've done with this type of technology before is to attach it to a robot and program the robot to manipulate the positioning of the laser beam around the complex 3D structure of interest such that we can build up a 3-dimensional survey. Okay, so we've got 3-dimensional laser vibrometers, but still typically they sit on a tripod and they're fixed, unless you've got $1.5 million, in which case you put it on a big robot and move it down inside your lab and make measurements across your vehicle of interest. But this is poor man's 3D scanning laser vibrometry, you might call it. But of course, you already need to have a 6 degree of freedom industrial robot sitting in the corner of your lab not doing anything, which at Loughborough we happen to have. So we did it by programming the robot, and then we did it for real. It's stop motion video, so it doesn't move at that rate. It spends a lot longer interrogating each measurement point. But we can drive the ball with a shaker here, and we can then position the laser beam to interrogate the vibration at these various points. And we're interested in modes that we can't typically measure by any other means. Silent modes, for example, which is like a ball skin torsional mode, which might be the mode that leads to significant introduction of torque when, for example, in a football, and I mean soccer context, the player heads the ball and he takes a rotation as a result of the fact that the ball's spinning maybe, and there's some artifacts in there that are interesting and we need to determine by doing vibration measurements. I'm talking way too much because I'm only into about slide 6 of 40, so I better hurry up. Another example of a measurement that I've done is putting a laser vibrometer on a UAV and flying this thing around, and I think this video starts and runs for quite a while, and we'll probably just need to skip forward to around about 30 odd seconds where we've got now this vibrometer, albeit tethered with power and data coming to and from it, respectively, taking measurements from a target. And this is literally the first measurement trial that we did. The pilot's just learning about the vehicle. We're indoors with no GPS support in terms of positioning, pointing, attitude and altitude control. So it's just a proof of concept. We will be able to do better. We'll be able to keep the laser beam on the target for longer and so on. Just to give you an idea of the kinds of applications. So in terms of the fundamentals of vibrometry, and I'll try to be pretty brief on this, what do we really measure? Fundamentally, we measure the Doppler frequency shift. What's Doppler frequency shift? We all know what it is, but this demo is quite a nice one that I've inherited from Chris Chapman, our very much esteemed technical support officer, and I've got his calibrated rugby sock in here, and hopefully this thing's going to play a sound for me. Actually, it's not at the moment. Why not? Yes, we didn't hit play yet. But Doppler frequency shift, we get quite nicely demonstrated as we do to our students in a lecture theatre. And so the concept being that if we can put light onto a vibrating surface and collect it in backscatter, the vibration velocity of the surface leads to a Doppler shift. And then we can sense that Doppler shift. We measure the direction of the velocity in the direction of the laser beam. But if the target vibration is complex, i.e. it's got 6 degrees of freedom of vibration, and maybe it also has some whole body vibration or rotation, is this thing that we measure still what we expect it to be? And I've done a lot of work historically around trying to understand how or what it is that we're actually measuring. So we've developed vector-based mathematical algorithms that describe the nature of the measurement, and we can apply them to a range of different measurement techniques that have grown in popularity, including scanning, which might be continuous if we move the laser beam continuously rather than from one point to the next. And also if an optical device is used to steer the beam, or indeed the instrument's on some sort of a vibrating vehicle or platform, and so it's leaping around, because we make a relative vibration velocity measurement, the difference of the velocity of the target surface and of the instrument. Typically we tripod mount this thing, but in increasingly interesting applications we want to put them on vehicles, maybe autonomous vehicles, and make measurements of other systems that are of interest to us. There are some practical considerations that we need to be aware of. LDVs are eye safe, they're class 2 laser systems. The blink response will prevent us from injuring ourselves, but don't stare directly down the laser beam. We use retroreflective tape for optimal signal level, which means that we maximise the backscattered light in the direction of the laser beam. That does lead to a speckle pattern in the far field, which if the point of incidence moves, as it will, because everything's moving, then we get that speckle pattern changing, evolving, boiling, transitioning across the photodetector, and we become sensitive to those changes in amplitude and phase of each of the individual laser speckles as a result of that motion. And so we need to take care of that. Sometimes that can be significant enough to mask the vibration of interest that we're measuring. We have to organise ourselves, traditionally at least, in terms of an optimal standoff distance to maximise the visibility. Coherence length of the laser comes into effect, and we have a reference beam that stays inside of the instrument. We basically need to match the path length of the target beam to the reference beam, so we have a coherence length and integer multiples of it, and when we mix the two laser beams back together on the photodetector, they need to have similar path lengths such that they will big together, and we get dark light as the target moves back and forwards. Increasingly, there are alternatives to that which don't have target and reference beams. Some cases like the LDV 5500, which makes measurements on rotating systems, both the target and reference beams go to the target and come back, so they'll always have done the same trip, they have always the same path length. I've mentioned the fact that we measure velocity in the direction of the laser beam. That's not necessarily as straightforward as it might sound, particularly when we have rotations. And I've talked about the relative vibration measurement concept. So anything that we use to steer the beam that might vibrate, we also measure that vibration. I'll maybe skip through some of the slides on like original measurement scenarios and more recent setups, so interferometer descriptions and so on. Those are in there if people are interested to get into it in some more detail. I can talk around these later. There are a whole now range of commercially available systems of various forms, many of which we have at UTS and have acquired quite recently, but there'll always be another laser vibrometer that we don't have. And the one that we're quite interested in is this thing here, this multiple vibrometer system, and we've applied for one of these through a LEAF grant the year before last. Once we've established the optical metrology capability, the vibration lab at Botany and the collaborations and funding that go with it, we might ask the ARC again if they'd be interested to fund or partially fund something of this nature. And there are a whole range of things that we can do with this, many of which are yet to be determined or discovered, but making measurements simultaneously rather than point to point is what this system is intended to do. So anything that you can't faithfully reproduce so that you can collect multiple averages at different points, you could make measurements simultaneously with up to 48 channels with this kind of a device. And there are some other manufacturers as well, in addition to Polytech, but they pretty much own the market. So around, again, I'll skip through this, but it's in here because it's important to put these measurement systems into context with respect to one another, but also with respect to traditional contact and transducer techniques. So some of the highlights that I'm picking out here are essentially to define a range of, like the maximum dynamic range, and we're good for, in some cases, up to 40 meters per second, which is a pretty fast, pretty high rate vibration, and displacement resolutions down to sub-picometer, right? So very sensitive, very high dynamic range, and very high frequency range. 24 megahertz is pretty much readily available, but we have systems that are good for up to gigahertz, 2.4 gigahertz. Clearly very, very low levels of vibration. We're not talking about 40 meters per second of vibration velocity at 24 megahertz. But they're tunable, they're definable. We can, they've got multiple range capabilities within the same device, so they're readily tunable or, can be configured to our particular measurement campaign that we're interested in at the time. I said contacting transducers, so here are some typical contacting transducers, and this is a comparison between dynamic range of traditional accelerometers versus introductory Polytech PDV 100 point and shoot digital vibrometer, of which we have 3 in the laboratory and we let students loose with, up to high-end shock accelerometers for high frequency, high acceleration applications, and our OFE 5000FS system, which is a fiber head, dual fiber head system that we also have in the laboratory. So you can see that they're comparable in terms of the applications at each end of the frequency range, like the useful or the interesting frequency range, which for human beings is between, say, around 20 hertz and 20 kilohertz. Okay. So some applications that are of particular interest to me, and I began life, not quite, but it feels like it now, getting interested in rotating system measurements. I've spent time in industry working in Formula One racing engine design. I grew up on a farm, so everything that we had was machinery orientated. This world fascinates me. I like to get dirty, I like to get grease under my fingers. I want to be able to design better systems. I want to be able to understand how systems vibrate. And so I was immediately drawn to this technology because of the possibility to apply it to these kinds of systems. And initially they were really differentiating themselves from contacting transducers because of this application domain. Okay, so there's some links in here which you could have a look through if these slides get circulated, and I'm quite happy to make them. public domain within this community at least. We can make measurements directly at the location of interest, and we've done this in Australia recently with a company in Queensland who wanted to validate torsional vibration in gas compression stages by making torsional vibration measurements directly from the torsional damper rather than having the crankshaft strain gauged at the other end of the system and trying to develop transfer functions that tell us or estimate what's happening at the torsional damper from the strain that's happening at the other end of the crankshaft. We've got some advantages with LDV for this scenario. Unlike other alternative non-contact techniques such as eddy current probes, we're inherently insensitive to target shape variation. What does that mean? We can make measurements on cams or geared wheels, provided we get light scattered by that target and we don't lose light off the edge of the target once per revolution. We can make a measurement effectively and we're insensitive to target shape variations. We demonstrate this to students in the lab. We have a little setup with a circular wheel and a square cross-section wheel, and we move this pair of laser beams from one section to the other section, and we look at the oscilloscope and there's no difference. My wife's desperate to speak to me. She doesn't realise how important this thing is. She'll have to wait. And that's not just about two beam instruments, by the way, that's single beam instruments as well. So instruments that make radial vibration measurements from shafts as well as dual beam instruments that make angular vibration measurements from shafts are both inherently sensitive to shape variation. For dual parallel beams, they're also inherently sensitive to translational vibration components. So they only measure angular vibration. In the context of torsional vibration, you know, the engine can be leaping around in X, Y, and Z at the same time as it's doing its torsional vibration thing, and we're not sensitive to that. An eddy current probe device or encoder wheel slotted disc scenario would be sensitive, of course, to all of those radial vibrations as well as the torsional vibration. And you can't tease the two things apart. Okay, and that was what attracted this organisation in Queensland to target this technology to try to solve their problems. And we had a great deal of success with that. This describes why. There's some maths on here. This describes why, I should say, that aside from the insensitivity to translational vibrations, for single beam measurements rather than dual beam measurements, we are sensitive, unfortunately, in the context of rotating systems, to the component in the orthogonal direction to that which we're interested in. So here I've got X and Y. If this thing just vibrates in X without moving, we make the intended measurement. If this starts to rotate as well, then we become sensitive to the component of the tangential velocity in that direction. Okay? If the system vibrates up and down too, essentially the tangential velocity changes position like this. Okay? And that's why we become sensitive to the product of the rotational frequency and the vibration displacement in the y direction. And that can be a challenge, but we can get around it by making multiple simultaneous measurements and having an independent speed measurement. And so we've done that and largely fixed the problem, albeit at synchronous frequency, where we just can't resolve because the content is lost in the Doppler signal of the light. And so there's some work still to do there, arguably, because synchronous frequency is pretty important in rotating shaft systems. Turns out not to be so significant in a V12 diesel engine, where 1.5 times rotation frequency is the most important harmonic, if you like. It's not strictly a harmonic, but we were quite pleased that for that reason this radial vibration sensitivity problem went away. Speckle noise is the other issue we have. I mentioned laser speckle previously. If that speckle moves, as you can see it doing here, as the wheel rotates, then those speckles move across the surface of the photodetector. We can't really see it with our eyes, it blurs out. But of course, an optoelectronic device can absolutely see those fluctuations. And we're only really focused on a small area of this on our photodetector. We look at one or two speckles. Each one of these speckles has independent amplitude and phase. We can fix the amplitude problem, it leads to signal dropout, but the phase problem we can't resolve. And in the measured signal, effectively for a wheel that rotates without much vibration, in the time domain the signal looks like this. So you can see these artifacts that repeat pretty much exactly once per revolution. Okay? And that in the frequency domain, or that time domain signal, which is known as pseudo-random in the frequency domain, has this characteristic. So essentially we've got peaks at the fundamental rotational frequency and higher order integer multiples. Okay? And this is exactly the same kind of spectrum that we expect from an engine, which might have half-order peaks as a result of the four-stroke combustion cycle, and then 2, 4, 6, 8 times as a result of the configuration of the engine. And we can't differentiate this speckle noise from the actual vibration of the system. So that remains unresolved. And so there's some things to work on there, and there's some ideas I have about how we might be able to fix that up with some research. And then I go on to compare torsional vibrometers, dual beam vibrometers, with other types of systems that are used for making measurements of angular vibration, i.e. eddy current probes and other such devices. What else can we do? We can move the laser beam around, and this was the other thing that I was interested in from very early stages, not just moving from point to point, but doing it continuously and being able to build up a vibration survey of our target of interest very rapidly. We have an increasingly wide-ranging availability of systems with orthogonal scanning mirrors in them to be able to manipulate the laser beam to go from point to point to point, but we can drive them with continuously varying signals and therefore sweep the laser beam around. And we can make some pretty pictures as well, some patterns which are quite nice, and of course, you know, it's interesting to have something nice to look at. These systems, from a scanning LDV standpoint, they offer us, as I say previously, high spatial resolution, a full field measurement campaign. We've got ever-increasing hardware and software complexity, so we can do some very nice measurements. We can correlate to numerical data. We can do model-based system testing and various other things quite happily with these techniques. If we move those around simultaneously, then we can scan things like circles. So we can track a point on a rotating bladed disc, for example. We can synchronize the scanning signals using some sort of tracking controller to an RPM signal, or an angle signal coming from the instrumented shaft, and then we can do things like amplitude modulation such that we're able to scan a line up and down a bladed disc as it rotates. This is a de-rotated version of this scanning form, and here you can see it being done for real with a long exposure camera. Similarly, we can modulate amplitude as well as phase, such that we can scan an area across a bladed disc as it rotates and immediately extract operational deflection shape information from these kinds of structures. And here you can see an old picture of me in the lab, or maybe not. Am I in that picture? No, I'm not quite. I've cropped myself out of that picture, but we did it back in 1999, demonstrated it to a few industries in the UK. And we've done it again at UTS as a proof of concept here, a proof of capability. And you can see the peaks in the spectrum here in the pink trace, which tell us about the nature of the shape of this blade as it rotates. And there's a slow-mo video where you can see it for real. So that's pretty cool. You know, we can get that information pretty much instantaneously from that time domain signal in the frequency domain. So there's a bit of interest around that that's slowly generating. What else is happening? We're taking vibrometers off the tripod. We're putting them on vibrating platforms. We're using them to augment sensor arrays for potentially autonomous systems. And this is really exciting for me, and I know a group of others within the room. This began life because we knew that vibrometers made a relative vibration measurement. So if this thing limps around, then we're sensitive to that. If we use a beam steering mirror, as is the case up in here, to direct the laser beam up from a horizontal orientation onto a difficult point to access within this single cylinder racing engine, then we're sensitive to that. I've got any audio? Yeah, there's some audio. Yeah, so you can hear this thing's pretty noisy, it's pretty aggressive. There was a genuine problem with vibration. The riders of this vehicle were coming off. You know, they were pretty distressed by the time they'd done a couple of laps of the circuit. And so could we determine, you know, by making some measurements on the dyno what the nature of the issue was? And so this lent itself as a very interesting application for this subtraction of vibration of beam steering optic, or indeed of the instrument itself. So here's a bit of a contrived experimental scenario where we're interested in the vibration of this display on this simulator system, which is on a 6 degree of freedom mast, the kind of system that we have just commissioned out at Tech Lab. And so we can fix this. Okay, so here's a single cylinder racing engine measurement. This is the vibration frequency spectrum of the mirror itself, and the dashed dot line is before correction, and the solid line is after correction. So half order and 1 times, we're mostly interested in these peaks in a single cylinder racing engine, or indeed any single cylinder engine. We don't get much of a benefit at 1 times, but we do get a useful benefit from doing the subtraction at half order. And so we'll choose to do that. And then we can do that with the traditional waterfall spectrum, and we can see the evolution of the half order peak and the 1 times order peak as we increase in engine speed through a sweep. If we look at on the tripod scenario with a 4-poster simulator measurement, then there's much greater benefit from doing that correction. So before is the dashed line, the actual target vibration, because in this case we happen to be able to put an accelerometer on the display, is the small dashed line, and the corrected LDV measurement is in red. So you can see it's very different before correction, but it's pretty much spot on after correction. So we get a pretty much 99% correction, and that's really powerful. Without that capability, we put them on things like UAVs, and we make measurements, and all we can actually hear is the vibration of the vehicle that it's on itself. How long am I allowed to go on for?
We started a few minutes late, so another few minutes.
Okay, so where am I up to? I've got around 8 slides, and a couple of them are section slides, so I'll just start to bring it to a close. Some other areas of interest for me are, what about if this happens to be a scanning vibrometer that's on the system? And so we've done it for single beams as well as for scanning vibrometers. In this case, you've seen this kind of an instrument before. This is a bespoke scanning vibrometer measurement. We've got a couple of orthogonal mirrors in here, and we've instrumented the front panel with some DC response accelerometers. We've got a target vibrating over here, again instrumented with a DC response accelerometer. So we know what the target vibration is. But what happens if we use these beam steering mirrors to manipulate the laser beam around? What's the correction need to be able to resolve that scenario? Here's a view from above. So there's my target up here. I've got two DC response accelerometers in here. I've also got another one down in here, which is intended to be along the line of the laser beam axis. And that's the key, really, is to be able to make a measurement somewhere along the length of the laser beam. And these results are currently in preparation for a publication which will be submitted later this year. But you can see from these plots, which look similar to previous plots, that before the measurement is corrected, we have a significant difference at low frequency in this case, because the vibrometer itself only really vibrates at low frequencies. Before and after, we get almost a couple of decade improvement, at least a decade improvement in the signal after we do that correction. There are some issues around some frequencies where we don't get such a good improvement, and that's as a result of the fact that the 2 DC response accelerometers that we use will mount to the front panel, which happens to be flexible itself, so the measurement that we make doesn't really give us the correct subtraction measurement that we need. So we use the single single accelerometer mounted on the laser beam path instead, and we get a proper correction at that frequency. And then we look at the scan angle, and if we scan an angle between -5 degrees and actually it's -4 degrees. I increased the axis to 5 so we can see all the data points. Up to 12 degrees, then you can see that there's a decent correction to be made across the angle range. For -4 degrees and 12 degrees, they're still relatively small angles. Okay, so there's not a great deal to be benefited from in this case by taking into consideration the angle, but there is a possibility with these devices to scan up to 30 degrees. Plus minus 30 optical degrees, at which point there is value in doing the correction properly, incorporating into the algorithm the scan angle of the mirror itself. What might we do in the future? And here are a few ideas that I've popped in here, and before I do that, just to give an idea as to what the capability is that exists currently and in the future at UTS. And so we already have in hand or in the lab these 7 systems, 3 of these, which we use in teaching and learning already. We've got one of these, and a rotational laser vibrometer, a couple of rotational laser vibrometers as well. To be delivered in about a month's time, a microsystem analyzer which makes measurements on a micro and nano scale of structures that in 3 directions with sub-micron spatial resolution, sub-picometer displacement resolution, and a scan range of plus minus 50 degrees in XY. So we actually put the sample on this bed and we move it around underneath this microscope system, which has got 3 independent laser vibrometers in it, and it resolves for us into 3 orthogonal directions automatically. And a PSV 500 macro scale scanning vibrometer, which is the first in the country that will have infrared light in there. So I mentioned previously that we have to take care with matching of path lengths, and we often have to treat our surfaces in retroreflective tape. With this device, it's high powered laser, it's invisible, And infrared is absorbed by the human eye, so because it's absorbed, it's still class 2 even though it's a 10 milliwatt laser. And then we can make measurements across distances of up to hundreds of meters without any surface treatment preparation and still get good high signal to noise ratios with huge dynamic range and high amounts of sensitivity. So that's a really exciting acquisition for UTS, and we negotiated a very nice deal from Polytech to allow us to purchase that system from them. And then in the future, as I say, I'd like to have another go at an ARC leaf, and it might take 2 or 3 more times of asking for them to give us a contribution towards a multi-point system. If we can demonstrate capability and really position ourselves as a leader in the region, and I think we can do that with our collaborations and the network that we have. And we'll do that by working on projects such as this and doing good jobs, excellent research, publishing top quality papers, and generating excellent outputs by way of PhDs, collaborating with industry on a whole range of projects and others that are not yet captured in here. And I'm really working hard to promote what we do here at UTS. That's what I'm focused on at Tech Lab, in addition to getting the LDV vibration lab up and running, and there's increasing amount of interest being generated. So that's pretty much me, and I'm going to wrap up here. Here's a few options for you to do a bit of after the hours reading if you wish. And I couldn't help myself when I got a notification from ResearchGate the other day to incorporate something with respect to this publication here, which was this. That's me.